All right, happy Saturday. We are going to work on chapter 3. Chapter 3, multiple linear regression. We are using Jeffrey Woolridge's textbook, Introductory Econometrics, a Modern Approach, the 7th edition. Now, for those who are taking my class, we are just continuing from where we left off last time. For those of you in the YouTube streets, well, welcome and jump in, eh? Okay, what's the agenda? I like to do an agenda. The agenda is we will look at the 4 assumptions for unbiasedness in the multiple linear regression. We'll follow that up with 3 ways in which multicollinearity may arise. We'll look at model over specification, where we're just adding in irrelevant variables, and we'll look at model under specification, where we omit a relevant variable. We'll think of the direction of the bias, size of the bias, and we'll look at some terms like upward bias, downward bias, biased towards 0. What do those mean? Then we'll look at the 5th assumption, homoscedasticity, and we'll say that, well, with the first 5 assumptions, we can write the variance of the OLS, the estimated OLS coefficient as sigma squared over sum of squares total in xj times 1 minus r squared j. And I'll get into that in a bit. We'll look at some examples, and we will observe that we can detect multicollinearity with the variance inflation factor 1 over 1 minus r squared j. And we will stop there. Okay, so here we go. I will use the slides, and I will pause and take some detours, right? So let's engage. Well, the first multiple linear regression assumption is linear in parameters, right, followed by random sampling, just like we saw in the simple linear regression. The third assumption says that there should be no perfect collinearity. Now, what does that mean, no perfect collinearity? And if you remember, in the simple linear regression, we saw that we needed some variation or enough variation in the explanatory variable. But in this multiple linear regression, we are looking at no perfect collinearity. Well, with no perfect collinearity, what exactly does that mean? You can take no perfect collinearity in 2. 1, you still want, well, 1 within variable variation, I'm talking about the explanatory variables, right? we want enough within variable variation. Within variable variation. And the second one will be between, the relationship between or among the variables, right? Relationship between or among explanatory variables. Okay, what do we mean by within variable variation? We mean that we want enough variation within our explanatory variable, within each explanatory variable. So enough variation within each explanatory variable. Okay, that doesn't look nice. Let me clean it a little bit. If you're new to this, when I'm within the zone, I'm writing surface. Okay, so enough variation within each explanatory variable. Okay, that should do. And then the relationship between and among explanatory variables. What do we want that relationship to be? Well, we want the explanatory variables we want to see some correlation, but no perfect correlation among them. Okay, so some correlation is okay, just not perfect collinearity between or among the explanatory variables, right? So we are ruling that out. Imperfect correlation is allowed, so that's what's written out here, and that is very much connected to what I'm terming relationship between or among explanatory variables. So when you take the third assumption, no perfect collinearity, you can see it in twofold. The third assumption, no perfect collinearity, can be seen in twofold. The first fold will be, well, we need enough variation within each explanatory variable. That's the first fold. The second fold is we do not want to see perfect collinearity between and among the explanatory variables. Imperfect correlation is fine. Some correlation among them is fine, just not perfect correlation. So perfect correlation will be 0.75 and above, right? Or 0.7 and above. So to check for no perfect collinearity, you typically have to do a correlation matrix, and in class I will show students in class what that correlation matrix may look like. Those of you joining us from YouTube, you can do a quick Google search to see what a correlation matrix looks like. Okay, so what are some of the ways? There are some 3 ways in which multicollinearity may arise, right? And this is coming from Woolridge's textbook. Now, I will scroll all the way down to find a place to write. Okay, so we can write that out. So 3 ways in which multicollinearity may arise. One is if one variable were a constant multiple of another. One variable is a constant multiple of another. So, for example, your x2 is just 2 times your x1. So, see how x2 is a constant multiple of x1? Yeah, these two will be super highly correlated. These two, meaning x2 and x1, will be super highly correlated. Okay. The second way will be if one variable were a linear combination of 2 or more variables, right? So, and when I say variables here, I'm not thinking of the response variable. I'm talking about the explanatory variables, right? So these 3 ways in which multiple collinearity may arise concerns the explanatory variables. Okay, so one variable is a linear combination, a linear combo of 2 or more variables. For example, x1 equal x1, x2, x2 plus x3. Okay. The third way, you could also have share A equaling 1 minus share B minus share C. Right? You could have this too. Okay, so the example 1, example 2. All right, the third way in which multicollinearity may arise is if the sample size was too small, such that the number of parameters that we were trying to estimate were larger than the sample size, such that such that number of parameters greater than the sample size. When you have this, it will be very difficult. It will be very difficult to have degrees of freedom remaining to do other calculations, right? So the ideal is to have your sample size larger than the number of parameters that you have. Okay. All right. So these are the three ways in which multicollinearity may arise, and if you are reading Wooldridge's textbook, you will see them. There we go. In a small sample size, if you had, let's see, this is expenditure, school expenditure, or the explanatory variable on beta 1 is school expenditure, and variable on beta 2 is average income, and the response is average scores or average test scores. So here in the second example, where you have share A and share B, it will be better to drop either share A or share B. Otherwise, there's an exact linear relationship between them, because the sum of share A and B is 1. Moving on, the zero conditional mean. In multiple linear regression, it is highly unlikely to hold. Although fewer things end up in the error, your backdoor path may still be open, just not widely open, right? So we worked on this in class. Now, zero conditional mean, what does that mean? Well, it means that your explanatory variables, there is no information in them about the mean of the error term. Now, in the error term, what could be there? Observed factors and unobserved factors. With the observed factors, it's easy. That is, if we can find those variables that are the observed factors, it's easy to find. It might be easy to find them and put them into the regression or the econometric model. But if they are unobservable and it's hard to proxy those, then it had better be that your explanatory variables contain no information about the average of those unobserved factors, such that there is no relationship between your explanatory variables and the unobserved factors in your error term. Then you can be safe, right? But the backdoor path is rarely tightly closed, even in a multiple linear regression. And so you can say that you have correlations, but not necessarily that you have a causation when you are interpreting your estimated slopes. So sure, it's more likely to hold, but please, it's better to assume that what you have found for your betas are correlations, not causations, right? More likely to hold if your explanatory variables are not correlated with those unobserved factors, and that's rarely the case. Okay, moving on. Can we overspecify the model? Yes, we can. We can include we can naively include irrelevant variables, which will then create a larger model, and therefore we end up with a larger sampling variance. When we include irrelevant variables, does that violate the third? And I'm going back to that third assumption, no multicollinearity. Does that violate it? Not in the strict sense. Now, if you go into Wooldridge's textbook a little bit, it will tell you it's not violated in the strict sense when you include irrelevant variables. However, the sampling variance, because as you include irrelevant variables, the model is larger, and so the sampling variance is bigger. You're going to get a large R squared. Now, the R squared will increase as long as you keep adding variables, right? With a large variance, the standard error is also going to be large. And so when you go ahead to do hypothesis testing, we haven't touched hypothesis testing yet in this class, but if you go ahead to do hypothesis testing about the relationship between your explanatory variables and your response variables, you will end up with small t ratios, and all of this might just lead to confusing and misleading information about the importance of those explanatory variables. So it has not violated no multicollinearity assumption. It has not violated that. What do I mean? Adding irrelevant variables does not strictly violate the no perfect collinearity assumption, but it creates a larger model, gives you a bigger R squared. I did tell you not to chase large R squared, but it gives you a bigger R squared. It gives you a large sampling variance, which then gives you a large standard error. And when you're doing hypothesis testing, which we'll cover later in chapter 6, there are issues with that. A large standard error gets you a small t ratio, which then misleads us on the importance of that explanatory variable. See, so there are some issues here to consider. Anyway, so overspecifying the model has some consequences. What if we underspecify the model? What if we omit a relevant variable? If we omit an irrelevant variable, there is nothing wrong with that. But if we omit a relevant variable, all of our estimated betas will be biased. All of them, yes. But, well, if we omit a relevant variable, we still end up with a smaller model. Sure, we still end up with a smaller model. We might have a smaller sampling variance. Yeah, but that's just because we have a smaller model. The problem still remains that we have omitted a relevant variable, and all of our betas, all of our estimated slopes are biased. So I have an example for us to follow. Oops, I think I went ahead a little too far. Here, yep, I have an example for us to follow. Let's assume that we have here the true model, y equals beta 0 plus beta 1 x1 plus beta 2 x2 plus u. So the true model contains both x1 and x2. Now, let's assume that we omit x2. So I want you to be thinking of a directed acyclic graph here, such that we have x1 impacting y. However, we have u, the error term, and in the error term, when we omit x2, x2 falls in the error term. Now, this is where I tell students in my class that the backdoor path is open because you have x2 and x1. They are going to be highly correlated. In this case, we are violating the fourth assumption because the explanatory variable x1 is correlated with x2 such that x2 is in the error term, and so x2 will inflate or will impact x1 so that the beta 1 hat that we estimate over the relationship between x and y is impacted by the influence of x2 from the error term. And how can I show that? I can show that mathematically. Let's work on this. So if we omit x2, we are estimating this model down here. Beta 0 hat, beta 0 tilde, y tilde equal beta 0 tilde plus beta 1 tilde x1 plus u tilde. That's what we've estimated. What is wrong with that? Well, x1 and x2 are correlated. So there is some kind of linear relationship between them. We can write that linear relationship as the omitted x2 variable equal delta 0 plus delta 1 x1 plus v. Delta 1 is the relationship or the correlation between x1 and x2. And if that correlation is statistically significant, then, well, they are correlated, right? So here we go. We can plug x2 equal delta 0 plus delta 1, x1 plus v into the true model. What are we doing? We are writing out what we estimated, this beta 0 tilde and beta 1 hat and beta 1 tilde. We are going to see what they actually are, how biased they are. So here is how biased they are. When we plug in delta 0 plus delta 1 x1 plus v in place of x2, and we redo this math, right? The math will go this way. Y equals beta 0 plus beta 1 x1 plus beta 2 delta 0 plus beta 2 delta 1 x1 plus I should just wipe that, plus beta 2 v plus u. Okay, so we are going to group things now. Y equals beta 0. I'm going to group that with beta 0 plus beta 2 delta 0. Okay, plus, now do you see this one has an x1, that has an x1? We'll try to group those, right? So we have beta 1 plus beta 2 delta 1 x1 plus beta 2v plus u. So this is y equals beta 0 tilde plus beta 1 tilde plus what did we use back here? U tilde plus u tilde. And so you can see that beta 0 tilde is equal to beta 0 plus some bias. Beta 1 tilde is equal to beta 1 plus some bias. You see? So when you omit a relevant variable, all your estimated betas are biased, and that's bad. That's really bad. So let's work on an example. What does this all mean? Let's assume that we have our true model. Wage is equal to beta 0 plus beta 1 times education plus beta 2 times ability plus U. Now, ability is omitted. We could proxy ability with, say, IQ tests, right, and have it in the model. But let's say ability is omitted. Now, ability is correlated with education. So if I write the DAG on that, the directed acyclic graph, and I'm trying to find out where do I write that. Let's try to write it up here somewhere. Let's see, education impacts wage, and then there's U. Now in U we have ability. Education is impacting wage, and that relationship between education and wage is to be estimated by beta 1 hat, right? It's what we use to estimate the relationship between education and wage. Now, ability is in the error term. Ability is correlated with education, meaning people who are more educated are also more able. People who are more educated are also more able. You see, more able people are more educated, and more educated people get higher wages. So it will look as if that higher education increases wage a lot, when in fact it's because more able people are also more educated, which is why that is driving beta 1 hat up. So what I'm saying is, and it's written right here, that the impact of education on wage will be overstated because the bias beta 2 times delta 1 is positive. Now, what is beta 2? Beta 2 says more able people get higher wages. And delta 1 says more educated people are more able. You see? So the combination of that, it's positive, right? Those two will be positive. I expect it to be positive. So the combination of that will drive up what beta 1 is supposed to be and make it bigger and overestimate it. Yes, so it will look as if people with many more years of education earn even high wages, but that is partly because people with more education are just also more able on average. You see? Is it possible to not have omitted variable bias? Yeah. If the omitted variable is irrelevant or uncorrelated with the included variable, then we are good. Then we do not have omitted variable bias. So there's this small thing of direction of the bias, right? The correlation between x1 and x2, if it's positive, and if beta 2 is positive, then we have a positive bias, which is what we had in this example. And I'm on this table here now. I'm working on this table here. This table 3.2. The bias is also positive if the correlation between x and y is negative or beta 2 is negative. Otherwise, we have a negative bias if the correlation is positive but beta 2 is negative, or the correlation is negative but beta 2 is positive. Then we'll have a negative bias. Now, what about the size of the bias? If the bias is small, we should not be too concerned about it, right? If the size of the bias is say 0.1% or 0.001%, that's not something I'd be concerned with that much. Oops. And now some important terminology. What is an upward bias? What's a downward bias? What does bias towards zero mean? I typically use a number line, right? So let's say we have the true beta here, and the true beta is positive, so 0 is out here, right? So the true beta is positive. If the biased beta is out here, and that's also positive, then we can say, well, the biased beta has overestimated the true beta, and so this is an upward bias. Otherwise, it's a downward bias. It's a downward bias if the true beta, if the biased beta underestimates the true beta. Underestimates the true beta. So on the right hand side, the biased beta overestimates the true beta. Now they are all to the right of 0, so these are all positive values, right? A downward bias is also known as biased towards 0, just because it's closer to 0. Do you see that? Okay, what if we have negative numbers? If we have negative numbers and so we are to the left side of 0, let's put that true beta here. And so the true beta is some negative value. Now, if our biased beta is to the right side of the true beta, meaning the biased beta made the true beta less negative, then we will call that an upward bias. And in this case, since the biased beta is closer to 0, it's an upward bias, or it's biased towards 0. Let me put a line between these two so we don't confuse them. If our biased beta was here, and it made the true beta more negative, then we say we have a downward bias. You see? Okay, so this is how to think that through. This is how to think that through. So where you have a positive values, positive beta, and here we had a negative beta. Okay. Where are we now? We just did all of this. We are moving on to the fifth assumption. Homoscedasticity is the fifth assumption. Well, with homoscedasticity, we are saying that as we take multiple slices of the data, so if your explanatory variable is education, slices of that data will be the different years of education, such as high school, some college, 4-year college, and maybe post-undergrad, right? These will be some slices of the data. Now, if you had, so I'm going over homoskedasticity for our class and to the benefit of our YouTube friends who may not remember this, but okay. So we have wage on the y-axis and we have education on the x-axis. Okay. So high school, some college, 4-year college, okay, post grad school. So these will be 4 slices of the data. Now, as education levels increase, we expect wage to go up like that. Homoskedasticity says for these 4 slices, or for the slices of data that we take, variation in wage is about the same. And so we will see that, sure, there is a positive linear relationship between education and wage. However, as we take multiple slices of the data, we will notice that there is similar variation in wage at every slice of the data, like this. This is homoskedasticity illustrated on a graph. So using different colors, right? For this slice of the data, which is high school, we see that there is this variation. There is this variation in wages. Let's use a different color. For this slice of the data, we see a similar variation in wage. For the post-grad slice of the data, we see a similar variation in wage. Homoskedasticity. The variation in wage across the different slices of the data does not change as education or years of education increases. The variation in wages across the different slices of the data does not change with education. Heteroskedasticity, on the other hand, again, we'll have for every unit increase in years of schooling, we'll still see education increase, right? Meaning there's a positive linear relationship between education and wages. However, we will notice a fanning out. So let me get my data slices. I'll do only 3 here. So high school, 4-year, post-grad. At the lower levels of education, we will see a smaller variation in wage. But at higher levels of education, we will see a larger variation in wage. And so you can see that at lower levels of education, that's the variation in wage, right? Okay. Now, at higher levels of education, do you see there's a wider variation in wage? There's a wider spreading out of the data points at higher levels of education. Yeah. So therefore, we are noticing a fanning out of the data points. A fanning out. So the other data points are going to be in here. Right, this is a fanning out of the data points. I need to extend to that other leg. Okay. And I should get rid of this one, but it's go. There we go. Oh, good. Fanning out of the data points. This is known as heteroscedasticity. Where the variation in wage grows with the levels of education. The variation in wage gets wider with the levels of education. That's heteroscedasticity. And the is sigma squared times some function of x. So sigma squared times some function of x. So variation as x increases will grow, will get bigger. You see. Homoscedasticity, on the other hand, variation is some constant number. It does not grow as the educational levels change. Okay. So, with these first four assumptions for the multiple linear regression plus homoscedasticity, we can write the variance of the OLS slope estimator like this. In the numerator, we have the variance of the error term, sigma squared. In the denominator, we have the product of the total variation in the explanatory variable xj and 1 minus the r squared of regressing xj on all the other explanatory variables and taking the r squared from that. So this is where you want to pause and remember what I said to you earlier on about multicollinearity, or what I said to you about no perfect collinearity, right? I said that it was twofold. The first fold was we needed enough variation within each explanatory variable. And the second was that we did not want any perfect correlation between and among the explanatory variables. This is what we are talking about, and that shows up in the denominator of the variance of our beta j hat. So this means that your variance of beta j hat will blow up if the variation in each explanatory variable was tiny. If there was not enough variation within your explanatory variable, the variance of your beta hat j will explode because that gets small. Now, if your xj was highly correlated with the other explanatory variables, then 1 minus that big number will be a tiny number, such that a tiny number times a tiny number in the denominator will blow up the variance of beta hat j. And what about the error variance in the numerator? Well, a high error variance will increase your sampling variance because there is more noise. Now, this other second item and third item I just discussed earlier on 2 slides prior, so please pause the video and go back to look at it. Here's an example of multicollinearity, and we are almost there. Let's say we have average score as the response. We have expenditure for teachers, expenditure for instructional materials as the second explanatory variable, and other expenditures. These are lots and lots of expenditures, but these different expenditure categories are definitely going to be highly correlated with each other. You see, so it will be difficult to detangle the impact of one from the other if they are super highly correlated. So the best thing to do with something like this is combine all the expenditures. Since the effects cannot be detangled or disentangled. And someone may think, wait, maybe we could drop some. Well, sure, but you can drop some to reduce the multicollinearity, but then you may fall into an omitted variable bias issue. This next slide is not coming by easily. Oh, here we go. So how do we detect multicollinearity? Well, we detect it by means of the variance inflation factor. And there's a rule of thumb that says that if the variance inflation factor is larger than or equal to 10, then you're in trouble. Otherwise, you're good. Do you realize that this looks familiar? Yeah. 1 minus r squared j was in the denominator of your variance of your beta hat j, right here. So variance of beta hat j is basically equal to sigma squared over SSTJ times VIF. So anyway, if your variance inflation factor was greater than or equal to 10, then you had a multicollinearity problem for sure. Again, multicollinearity is not a strict violation of the third multiple linear regression assumption. That said, we did not want any perfect collinearity among our variables. I went over the reason why, and I'll go over it one more time and we'll stop. The reason why multicollinearity is not strictly violated here is that, well, when you have more variables in there and there is some multicollinearity issues, dropping those variables will get you down to a smaller model. But if that variable you drop is a relevant variable, then you end up with an omitted variable bias problem. Now, when you have an omitted variable bias problem, all your beta estimates are biased. And that's a worse case scenario than just leaving your variables in there, even though they are highly collinear with other variables. I'll stop here and I'll talk to you later Yeah, it seems it is, exchanging one problem for the other, or keeping the less serious problem. We'll talk more about this in class next time. Have a good weekend. Thank you for joining me. Hope it wasn't too boring for you. Even if it was, well, there will be an exam, so study hard. Okay, Dr. T.